part 4. It's all about flash memory cell, right? What we talked about last class. Today's class we will talk about on the memory organization, how a flash array is structured, and how we read and write from the entire flash. Okay, so all those details about flash array will be taught today. So this is my plan material to cover. So we will talk about the physical structure and how logically we read from the NAND flash chips, right? What are the logical units for read, write, and erase. And then we will go in the specifics of the read, program or write and erase operations. Okay, so these are my plans. Okay, so this is how, if you take look of a die, right? NAND flash die. So, for example, if you decap your SD card, inside the SD card you will see a shiny picture like this. Shiny is because this is silicon wafer, right? So it reflects light. That's why it looks like this. Now, distinction here is, so this is a real chip, real photo from 64-layer 3D NAND chips made by Toshiba. This is the paper from where I got this cartoon, right? So here, important things to note is there is a plane 0, plane 1. So these are the two planes where your memory array will be laid out, okay? So you have different word line, bit lines. As you always know how a memory structure looks like, there will be a bunch of word lines which are row, bit lines which are column, and that's how, so this is the region where plane 0, where you have one part of the array, plane 1 is another part of the array, and in between you will have row decoder, then page buffer, column decoder, this will in the bottom, and this is your peripheral circuits, right? So in NAND, peripheral circuits are huge because you need charge pump, right? You have to increase the voltage. From USB supply, you will be giving maybe at most 5 volt, right? Or maybe 3.3 volt. We have to amplify that voltage internally to 20 volt. So we need charge pump, we need sense amplifier, right? To sense a bit, decoders, as I said. So these are the part of the peripheral circuits. So it takes around 10 to 15% of the footprint, 10 to 15% of the real estate of your wafer with the peripheral. Okay. Any questions here? Yeah, so if you save this peripheral, of course, you will save money because, so there are new chips, right? New chips comes with peripheral under the array, like a 3D structure. So you bring in peripheral under the array. So if you take a bare look of the die, so this is the die, you will just see the plane 0 and plane 1. Peripheral you will not see in the recent chips. Recent chips, peripheral is done under the array. So there are many innovations happening in NAND. It's active field. Bit density is growing every year. That steady bit density increase is still going on. So maybe in the next class we'll talk about some of those innovative trends. But today we'll talk about the fundamentals, how a chip or how a NAND flash die looks like. How are these memories arranged in a row and column fashion, and how we access them page by page. Now, if you take a simplistic view of this picture, right? So how, or what is the hierarchy of logical units? One is the die. This is your die, which is the blue color here. The entire thing, top level die. And then one level down is a plane. Inside the plane, you will see block memories or memory bits are arranged in the chunk of blocks. So all the blocks are like identical units. Now, inside the block, there will be page. So you read page by page, not word by word, right? Word is, say, 16-bit, 32-bit word, right? It's a small word that we read from, say, random access memory, like SRAM, DRAM, we read word by word. Here, we read the entire page. The page can be large, like 16 kilobyte. This is the standard size of a page, 16 kilobyte. Right? So lots of bits. You read at a time and you ship it. Because this is used for mass storage, right? It's not a random access memory. This NAND flash is for mass storage device. You are supposed to store large volume of data, right? It can be your video file, audio file, or it can be text file, but at the end it will be stored in the bits in these pages, memory pages. Okay, so if you look at inside a block, how the bits are arranged, so this is the cartoon of a block. Okay, these are flash cells, flash memory cells. So we put 3 lines here just to show there is a floating gate. It's a floating gate cell, so you store information on the gate stack in the form of charge. But this is not floating gate, this is the select gate. So this says select which block you want to select. So the top and bottom are the select gates. In between you have memory cells. Memories are organized in the form of word line. This is one cell, bunch of cells in parallel, right, which are connected in a word line, forms a page. So you read and write page by page. That's one important thing. But you can erase one full block. You remember we talked about flash erase, right? The name flash comes because we erase a lot of, or all the word lines together. There is no command which will allow you erase one word line. There is no operation in flash die or flash chips which allows you erasing a single word. You have to erase all the word line together because all the cells that you are seeing in a block, they share the same substrate. And erase happens through this substrate. You give a high voltage to the substrate, all the word lines will be grounded, you erase it, right? While programming, substrate will be ground, you change the voltages on the word line, high voltage in the word line, you program word line by word line. You read word line by word line, but you erase entire block together. And that causes a lot of difficulties in a system management. This mismatch in the read, write, and erase granularity will cause a lot of issues I'll talk about in the coming slides, but this is one thing to know that we read and write page by page, and page size is a lot, 16 kilobyte, right, 16 KB. You can find the number of bits. So that many bits or that many size of data you write together on flash. And erase takes place on an entire block. Any questions here? Okay, so now why the name NAND comes? Because this is a NAND chain that you can see how the cells are organized. These are not independent to each other, they're series connected. You see only one word line horizontally. Bit line is only on top. There is no source line. If you recall your 1T, 1C, DRAM or SRAM, right? They have ground terminal. So here, for example, this cell has no ground. You see, so and why they do it? Because to optimize the density. Because if you have a ground line or source line going in parallel, you will take up a lot of area. So you want to achieve 4F square, right? Very compact footprint so that you can pack more and more bits. Because density is the main metric here, right? For NAND flash. How dense the bits are. So, okay, so this is one important distinction that if you want to go to ground, you have to basically turn on all the cells in one column, right? This is the feature of a NAND, CMOS NAND gate, for example. All these NMOSes are connected in series. So that's why the name NAND memory came, just to tell you the origin. But suppose if you look at whether this cell is conducting or not, right? If you want to find a cell is conducting or not, you have to turn on all the other cells in that series. Only then bit line to ground path will be conducting. So, so that's a little different how you read and write, and we'll talk about that in more detail as we go forward. Now, the question here is this granularity mismatch, that you read and write page by page, but you cannot erase entire page, right? You have to erase all the pages together. What is the problem here? So for example, say this is one block and you have to, or you want to erase page 0. How will you do it? If you cannot do page by page erase. Any thought? Or so you want to update this page, right? So you wrote something which is stored, now you want to update a page. How will you do it? An area. So you have to transfer those blocks, right? For example, you have to transfer all those valid pages. because in a block there will be thousands of pages, right? So only one page you want to update. So 999 pages you have to transfer to a new block, and then you can issue an erase. Then the block will be erased. So that's how you can, to destruct, right, or to erase one page, you have to erase all the pages. That's the only command you have for erasing. And then you can update this page and write on the new location. But all the valid pages has to be transferred. So that's a hefty operation, hefty overhead. So many times what system does, they just say, okay, this page address is invalid, so data is still there, right? Only thing is, logically, they say data is gone. So that's one security issue. For example, you think from your thumb drive, all the sensitive files are gone, because you have done an erase, but actually they're not erased. They're logically invalid, but if somebody gets physical access to your thumb drive, they can recover the data, because the data is still lying in those invalid addresses. Okay, so that's one security issues with NAND flash, because this is what I'm showing is hardly done, because you have to, you cannot just for single page erase, you cannot write 900 pages on a new location. This will take a lot of time, right, and a lot of energy as well. So yes.
So you're saying the data is just overwritten?
So overwrite is not possible, because you can only write works only on erased page. So overwrite is not possible, which was there for DRAM or SRAM. You can in place update, right? You can update a page in place. So there was no erase command. But for NAND, unless a page is erased, you cannot write on it. And erase happens in an entire block level. So that's looks like a simple problem, right? Granularity mismatch, but it causes a lot of system pain, I would say. So and that's why NAND controller design is so sophisticated, right? You have to manage all those granularity mismatch. You also have to manage the errors in the memory bits, right? You also have to manage the finite endurance. If you keep using one block again and again, that block will die. So you have to maintain that all the blocks are aging at the same rate, so that as a user you don't see the failure. So those are system functions. So NAND controller actually is very, very sophisticated. Separate companies make them. For example, Marvell Semiconductor just make NAND controller. SanDisk, for example, makes just NAND chips, or Micron makes NAND chips. So yeah, if you open up your SSD, you will see there is a square-shaped big chip. That's where the NAND controller goes in. Okay, so that's just to tell you. Maybe later in the course, if you have time, I can give you an overview of NAND controller and some system functions, how all those goes in. But today's class, we'll stick to basics. Basics here is read, write, erase, how those operations are performed at an array level. Okay. Now we saw the physical structure of a NAND chip. There is a two plane, there is a peripheral. Now let's look at logically how we'll see NAND. Okay. So this is or sometimes it's called logical scaling. Scaling, you understand, right? Scaling is to make things small so that you can pack more bits. So to increase the bit density. This is called physical scaling, making things small. But in NAND, there's something very interesting. It's called logical scaling. But okay, I'll not touch my hardware. Hardware will be exactly the same. The cell size will be exactly the same. Still, I can pack more bits. Right? So that's called logical scaling. So let's explain this part a little bit more. So here, this is a cell, a flash memory cell, right? So you have blocking oxide, tunnel oxide, floating gate, where electrons will be stored like this. If there is no electrons, it is logic 1, because threshold voltage is low, it will conduct if you put a reference voltage, right? If there is electrons in it, we say threshold voltage is high, it will not conduct, it will represent logic 0. Right? So that's how we store information 0s and 1s. So this is single bit per cell. A cell is storing either 0 or 1. Right? So if it is storing 0, its threshold voltage is high, the red distribution. If it is not storing any electrons, then we are saying it is storing logic 1. Right? So, and then we apply a reference voltage in between, which will distinguish if a cell is erased or if a cell is programmed. And that's how, at a parallel, all the cells that are connected to a single word line, you know what's the status. Are they conducting or not conducting? Okay, so now what is logical scaling? Logical scaling means, okay, this cell, same cell, here I understand 1 bit, 0 to 1, but it can be also storing 2 bits. It can be also used to store 3 bits. Same cell, no change in the cell structure or physical geometry of the device, right? It is just by controlling how many electrons you want to inject that you can control. If you can control that precisely, then you can bin, right? For example, if you want to store 2 bits, how many threshold voltage levels you need? If you want to store 2 bits in a cell. So if you want to store 1 bit, you need 2 threshold voltage level, right? 2 to the power 1. If you want to store 2 bits, you need 2 to the power 2, right? 4 threshold voltage levels. If you want to store 3 bits, 2 to the power 3, 8 threshold voltage levels. So you have to bin the threshold voltage, right? So if you can control the threshold voltage in such a precise manner, then you can store multiple bits per cell. And that's exactly what we will do. For example, here, this is single bit per cell. This is multi-level cell or 2 bit per cell. It's called multi-level cell. And then you have triple level cell where you need 8 different threshold voltage levels. Okay. Now, what is interesting here is this programming window, right? Or many times it's called memory window. The range from where you can program, the highest program level, that does not increase that much. Because if you can increase this highest program level, you can space those distribution sparse. But what limits you? I mean, what prevents you to increase the highest programmability level? What is the problem if I increase the programmability level? It's a double.
The oxide.
Yes,
You
and
have to have more voltage.
more voltage. Because already, right, you are using charge pump, already you have in amplifying the voltage to 20 volt. If you want to, so highest VT level will be around 7 volt, maximum you can go, right here. So if you want to go for 10 volt VT, you need to really increase your charge pump strength a lot to amplify the voltage. So yeah, so highest VT level and lowest VT level is around 0, so here is VT. So that range is pretty much fixed. That means the challenge here for multi-bit level is you have to narrow the distribution as much as possible. Because one distribution superimposing with another will cause error. Because then you cannot distinguish, right, which level it is. So single level cell will have highest reliability margin, right? So if you look at here, yes, you can go increase the density, bit density 3 times, but your reliability will be poor for 3 bit per cell. Not only reliability will be poor, even your performance will be poor because it will take longer time and energy to program this memory. Right? Because you have to spend a lot of time to shape the distribution to be narrow. Okay, so that's the trade-off: density versus reliability trade-off, or density versus performance trade-off. Right? So yes, triple level cell will come with lower price because maybe 3 times lower price because your hardware, real estate is same. Real estate for, say, this is 1 gig SLC versus 3 gig PLC is same. Because every cell is storing 3 bits. So instead of 1 gig, you can buy 3 gig on the same price. But you are paying in terms of lower reliability. You are also will suffer in terms of performance. Questions, comments here? Anything that intrigue you? Yes.
Why does it go like 11010010 instead of like order?
So that's a very good question. There is a reason, very strong reason. The reason here is, say, it is called Gray's encoding. Okay, there is a pattern for it. For example, if you go from say 00 to 11, problem is if a cell threshold voltage drifts, right, 2 bits should be flipped because you are going 00 to 11 or 01 to 10, right? So you don't want 2 bits to be flipped because of some cell mistake. So here, right, only 1 bit is changed. You can see 11 goes to 01, 01 goes to 00, 0 goes to 10. So this is between 2 adjacent state, only 1 bit position is different. And that is intentionally done so that even if there is some error happens, error means error will happen in the physical world, right? Threshold voltage sensing can be error in. Then only one bit will flip, not two. And that's called garage encoding. That's the reason. Yeah, this is a good question. So let's look at this logical scaling a little bit deeper, right? So for example, how we will write, how with here single level cell, I understand. Okay, I want to write, I'll give a programming pulse. It will be programmed. Otherwise, I'll not. But here, right, we have to shape up the distribution. So let's look at first the logical page structure of an SLC memory. SLC means single level cell. Suppose your programming voltage VT is 2 volt, your erase voltage is 0 volt. Then if you want to store 1001, then this first cell will be programmed or will not be programmed, it will be at erase state. So its threshold voltage will be 0, less threshold voltage. Yes, second cell, the red one, I want to program because I want to store 0 here. So we will increase this threshold voltage by injecting electrons. So electrons will be injected in this second cell and third cell, not the other two. Right? So that's how I will program array. So after programming, if you measure the threshold voltage, you will see this is the threshold voltage values in the 4 cells. Right? So this is not surprising because it's SLC. You have 2 different threshold voltages, and you can read by applying a reference voltage which is in between 0 and 2, say 1 volt, and then when you apply this word line voltage as 1 volt, this will conduct, this blue will conduct, red will not conduct, and that's how you get the answer 1001. So this is how read and write happens in a SLC memory. Yes.
For multi or 3D line cell,
Mm-hmm.
is it a matter of time voltage is applied?
Yes, this time is also will be higher, and also you have to do precisely. So that's program and verify. There will be verification will be done. So in this class, I'll go to that level. Yeah. So at the end of the class, I'll show how exactly multi-level cell are programmed. But I hope SLC logical page structure makes sense. So based on your logical data, you will write, and also you will have some out of bound code to store your error correction code. Whenever you write data for a page, that's 16 kilobyte, even if some bits get flipped, using error correction code, you can correct it, like Hamming distance code, right, or Hamming code. So LDPC code, BCH code, there are several codes which can correct some percentage of bits, but still it is quite low, around 0.1%. That means 1 bit out of 1,000 you can correct. So because if you keep code word long, then you are killing the density again, right? Because every page is 16 kilobyte, at least 2 kilobyte is reserved for code word. So when we see, right, for example, in our research group, we can write all the bits in a word line. This is actually 18 kilobyte. The reason is whenever an user writes data, they will write their data and they will also write the code word. So that if there is a bit flip, they can correct it. And all those things are done by the system, NAND controller. So that's the more sophisticated chip that will calculate this code word. NAND will just write whatever is given to write. Okay, so that's your SLC storage, and this is the threshold voltage of median threshold voltage. Now, we always show distribution because, as I said in the previous class, right? Suppose you want to program with 5 electrons, but not all the time you can inject 5 electrons. Sometimes you will be injecting 4, sometimes you will be injecting 6. So that's why there will be some over-programming, some under-programming, and distribution will be, there will be broadening of the distribution. Even though your target is 2 volt, you will be having a distribution. And you see erase distribution is even wider. Because erase distribution will include this process variation. When you fabricate memory bits, right, there will be always process variation. So erase distribution is the widest because this is uncontrollable. But program you can control. Suppose the inherent VT is a little bit high, then you can inject less electrons, right? So because here, when you're programming to 2 volt, you can control how many electrons I can inject. But when it is erased, you don't control. It is the natural variation comes in. So typically erase distribution will be wider, which reflects the manufacturing variation, and program distribution depends on how you are programming it. You can make it really tight by reducing the step size of your program. So we'll talk about it a little bit more, but I hope this distinction you take a look, and you apply a reference voltage. So anything below reference voltage will be 1, above 0. So due to the cell-to-cell variability, there is 2 distribution will be formed after programming. And that's why you need to keep them far apart, so that even after distribution widening, you can still distinguish them accurately. Okay, so that's about SLC, right? So SLC, yes, density is the least, but is the most reliable. You can go endurance cycle like 100,000 cycle. 100,000 is the like maximum. A drive, 100,000 times you can use. Data retention 10 years. Read latency 25 microsecond, around 20. So it is microsecond, like no more nanosecond. But even though it is microsecond, you need to understand you are reading 16 kilobyte together. So per byte, it is not that low. Per byte is still nanosecond. But yeah, you are reading 16 kilobyte, but still it is slow. And then programming is even slower. It's hundreds, 200s microsecond for programming one page. Right, so that's the slowest memory. That's why we have SRAM, DRAM, flash. Right? These are the 3 main pillars of all storage and memory applications. Any question here? Okay, so now let's look at how multi-level cell works. So this is your multi-level cell. You have 4 distinct VT levels, right? So you are storing 1, 1, 0, 1, 0, 0. So this is gray encoding, right? So you are storing 2 bits. That means even if every cell, this is one cell can have 2 bits. So one cell can have in all those 4 states. We call them L0 state, L1, L2, L3. These are level. L0 level, programming levels, which will be say close to 0. This will be close to 2, 4, 6 volt. So that's how we bin the threshold voltage, and we can apply reference, right? So here, now question to you: if you want to read, say you program those bits. Now you want to read the LSB bits. How many read reference you need? How you read it? So question here is L0 is a 0 volt threshold voltage. Yes, L1 is 2 volt, L2 is 4 volt, and L3 is at 6 volt. How you will read the LSB bit? Which voltage you will apply? Yeah.
Would you apply 3 different voltages?
Absolutely, that's a very good answer. So you can see here, right? L1 is at 2 volt, L2 is 4 volt. You will apply a reference here, and that reference can be at 3 volt. Because if you look at here, right, L2 and L3, doesn't matter, you are at 0. LSB bit blue is 0. So whether a cell is programmed in L3 state or L2 state, it represents 0. Whether a cell is programmed in L0 or L1 state, it represents 1. Right? So these 2 represents 1 for LSB, these 2 represent 0 for LSB. So that means if you just apply one reference here, so one sensing is good enough to decode LSB data. How about MSB? Can you do it in one sensing? No. You have to read 2 sensing. So you have to apply one sensing here. If it is conducts, then it is definitely 1. If it does not conduct, you are not sure. It can be 0 or it can be 1. So you have to apply another one here at reference 2. Right? And then you see whether it is conducting or not. If it is conduct, then it is 0, and then 1. So first you do reference 0 and find who is conducting. You know that this is 1. You decode that part. And then you do another reference with F2 and see who is not conducting and put them as 1. Okay, so only one sense operation is needed for LSB, whereas 2 references are needed for MSB. So MSB bit decoding is slower. So that's why you can see latency. Read latency is in a range. 25 will be for LSB bit, whereas if you want to decode MSB bit, you need higher time. Okay, so that's what your latency depends on what bits or which page you are decoding. Your endurance cycle is also less because now you don't have enough margin, right, between 2 states. Unlike SLC, you now have multiple states, so margins are less, and also you are programming to certain higher VT value. Right? So when you program to a higher VT value, you apply higher voltage. That will also cause degradation faster. your program latency is significantly slow. It's millisecond now, 1.8 millisecond. Because it is not easy to shape up this distribution in a nice, tighter fashion, right? In SLC, okay, you can have too broad distribution, that's okay. But here, you cannot make L1 broad because then it will take up area of L2, position of L2. So you have to shape up the distribution, so that means you have to do a lot of finer step of programming. So that's why program latency is high. Okay, any question here so far? So now let's look at then how exactly an user will write data. So as a user, right, we don't care about this is MLC, TLC, or QLC. Right? We'll say, okay, I want to write this data, I want to write this data. I'll send the bit stream. So let's assume this is the bit stream. The user sends first the LSB bit stream, then the MSB bit stream. So user doesn't know it is LSB or MSB. The chip will consider, right? So it gets first 16 kilobyte. It knows that okay, this will go in the LSB page. Then another 16 kilobyte. It goes okay. This will go to the MSB page. After that, it will decide what will be the state of each cell, right? So for example, after this, what will be the first cell state? It will be L0, right? 1, 1. Both are erased, so it should be going to L0 state. Second one, 0, 1, go to L1 state, 0, 0, L2 state. So from the user data, the NAND internally will find out what state the cell will be going. So let's assume here, this is MSB. So now I want to program this bit, this bit, this bit, right? So I have to make a decision. Should I program it to 1 volt, 2 volt, 3 volt, 4 volt like this, right? So based on the state encoding, you will program. For example, here, you will program it to 0 volt, you will program it to 2 volt, you will program 4 volt, 6 volt, and so on. So based on the user data, the NAND will decide which threshold voltage this cell will go. And that's how it will program. And how it will control the threshold voltage? By injecting charge, right? So here, so L0 state, there will not be any charge injection because it is a 0 volt. L1 state, this is the L1 state, 0, 1. So it will cause 2 electron. Let's assume 1 electron cause 1 threshold, VT equal to 1 volt. So that cell will go to 2 volt. This cell, because of 4 electron, will go to 4 volt. This cell having 6 electron will go to 6 volt. So that's how the injection statistics, right, or charge injection will be controlled to make sure it goes to the desired VT level. And that's how you store 2 bits of information, right? So to store, you need 2 pages of data. So user will send 32 kilobyte, right? First 16 kilobyte will go to LSB page, and next 16 kilobyte will go to the MSB page. So like that operation. This is very important to understand. Even though they are sharing the same word line, but this data is first sent, first 16 kilobyte is blue, next 16 kilobyte is in red, and internally, when programming happens, they will dictate where the cells are programmed. Make sense or no? Okay, so let's look at a few concrete examples that will make more sense. So for example, here, this is your all these 4 different levels, L0, L1, L2, and L3, and these are the median VT values. Of course, there will be some spread because you cannot precisely control the threshold voltage or charge injection. For LSB read, you just apply a reference here, ref1. So anything on the left, anything lower than ref1 are decoded as 1. Anything above reference 1 will be decoded as 0. So in one shot, you will get the blue data. Just one sensing operation. Right? So at 3 volt you apply. So whether you are in L0, L1, you will be 1. L2, L3 will be 0. Now for MSB, you need 2 referencing, and that's how you decode the MSB data. So MSB data will take longer time. But more important thing that I want to share here is that you can store 2 logical page of data sharing the same word line, right, which is not possible, say, for DRAM or SRAM, where a single logical page or a single word line will store a single logical data. Right here, you can two independent bit stream, right? One bit stream is in LSB page, another bit stream is for MSB page. They are sharing the same word line. That's why they are called logical shared page. Okay. Now look at how exactly we program. Right? For example, can I program one page by one page, or do I need to program both of them together in this structure? Suppose user stops after giving LSB data. Do you think NAND will not program that? You understand, right? So we said that we need 2 pages of data. LSB page 16 kilobyte, MSB page 16 kilobyte. But suppose the user just gives 16 kilobyte. So what will happen? So you do programming actually step by step. For example, at the beginning, everything is 0, right? Or sorry, L0, which is erase state. So let's assume that I want to program only 4 cells. So let's assume your page size is 4, just for illustration. And you want to write 1100 in the LSB page. What you will do? You will program LSB page like this. You'll go for L0, you'll skip L1, you go to L2. Because for LSB, right, L0 and L1 both represents 1. So you go to L0 and L2, now LSB is written. But if you are in L2, LSB is 0. If you are in L0, LSB is 1. Now, if you want to do MSB data, right, what it will do, it will split it. Right, so it will split this way. If MSB is 0 and LSB is 1, it will go here. And if LSB is 0 and MSB is 1, it will go here. So programming can be taken or can take this step by step. You first write the LSB data in the form of L0 and L2, and then split L0 based on MSB data, split L2 based on MSB data. So that's how we can do all 4 or all the 8 bits in 4 cells independently. Right? You write independently LSB data, and then MSB data depends on LSB, which state it will go. Make sense? So you'll be tested in quiz and all some of those ideas, so it will come back. But in general, it's quite interesting concept, right? So you can increase the bit density without squeezing the hardware. Okay, now how will read? For read, again, as I said, you apply first 1 reference. For LSB read, you just need 1 reference VREF. And whoever is conducting, you put them as 1. Whoever is not conducting, you put 0. For MSB read, decoding MSB read will take 2 steps. First, you apply VREF 0, see who is conducting, that is already 1. Who is not conducting, for that you apply another VREF and see who is not conducting, that will be 1 and others will be 0. So it will happen step by step. So NAND always like to see who is conducting. But the moment it is conducting, right, decline will be discharged. Sense amplifier will play. If it is not conducting, it doesn't know what to do. So first step, conducting, you find, so okay, this cell is conducting for MSB read. So it is decoded as 1. Next step, you will see who is not conducting. That will be decoded as 1 in the next step. So that's just different convention. Okay, so that's how we do step-by-step read. So MSB read will take longer time, almost double, not exactly double, but yeah, one is 25, another will be say around 40 microseconds. Now, if you can extend this idea for TLC, for example, TLC, you can see your endurance is maximum 1000 cycles because you have to use 8 states, right? And your highest VT level remains same, pretty much like 6 or 7 volt. Your lowest VT level remains same, close to 0 volt. So your memory window remains same. And to divide this window in very precise level. And that is the magic of programming algorithms, which I'll be talking in the coming slides. But it becomes increasingly difficult. When I was working in the industry, making TLC was difficult. Right? We had product, SanDisk had product. Most of the USB drive or low-end drives was TLC. Because TLC is cost-effective, right? You store 3 bits per cell. But now, all the drives that you buy QLC, 4 bit per cell. Right? So when I was working, 4 bit per cell was difficult because TLC itself was difficult. Making those margins is harder. You will have a lot of errors just after write. Okay, so yeah, so you can see data retention is low. It's no more 10 years because the states little bit drift will cause error. And with error correction code, you cannot correct any amount of error. You can maximum correct maybe 0.1%. Okay, so your read time also increases. It's no more 25 microseconds because how many references you need, right? You need to understand that part. How many sensing operations you need. And then programming also very, very high. See you go. So this is the TLC, and this is your, say, one test design. For example, in one of the homework problem, I think I asked you to design the median VT level and the reference level. These are the two important quantities that you need to design for TLC, QLC, or MLC. So for example, your minimum voltage is 0, maximum voltage is 7, right? This is the spec. Now you want to design TLC with equal space distribution. So then all the medians will be 1 volt and VREF will be in between. So 0 and 1, 0.5, 1 and 2, 1.5. So that is the rough calculation for that. So how many read reference you need to decode a TLC memory? Say LSB page, LSB bit. If you want to decode LSB bit, how many references you need? Just one. See here, right? So if you see blue, all are 1. So it really doesn't matter which state you are for LSB point of view, right? It is all 1, it is all 0. So you put a reference blue here, you know your LSB page data. For MSB, you need 2. VREF 2 and VREF 6. Right? You have to apply here and see who's conducting. Again, you apply here and see who's not conducting. Right? And based on that, you decode 1. For MSB, the most significant bit, which is represented in red, will require 4. So that will require longer time. Decoding MSB page will require longer time. So yeah, so now you see, reading, writing depends on what page you are reading, what page you are writing. And based on that, your time should be varying. So reading LSB page will be the fastest, yeah, close to like SLC mode. Reading MSB page will be the slowest. And this encoding is very important. This is not the unique encoding. You can come up with different encoding to balance read time for different pages. Okay. Any question here? Okay, so next level is quad level system, which is now the state of the art. This is the state of the art. You have 16 different VT levels because you want to show 4 bits. There are the 4 different pages, right? So you can see distribution has to be really narrow. So let's think about you have window of 0 to 8 volt, and you have to pack all those 16 bits. So every state, maybe maximum can be 0.5 volt within this range. So controlling within 0.5 volt, that means you really have to count how many electrons you're injecting. So that's how difficult it is. But yeah, industry is making it, and all most likely whatever SSD you are using will have QLC inside. Now we can do fractional storage. This is one of the research questions we ask in our group. Can I store 1.5 bits instead of 2 bits? Or can I store 4.5 bits? Answer is yes. You just think about 2 cells, right? So far we talked about 1 cell. 1 cell in multiple levels. But if you think about 2 cells and I want to store 3 bits, then it is per cell 1.5. So that's how we can think about fractional storage as well, and you can come up with your own encoding. For example, if you want to store 3 bits per 2 cell, then it needs 3 distribution. Every cell can have only 3 distribution. This is advantages, right? You can use spacing between them, and then you can encode this encoding like this. Okay, odd bit, even bit, right? 2 consecutive bit I will consider as 1. And 1 bit I can put in one of this state, another next bit I will put one of this state. And the combination will decide if both are in, say, in L1 state, then I'll say 3 bits are stored in them. So this is just encoding, logic encoding you need to define your bit state. For example, this is your user data. You combine these 2 bits together, 2 physical cells together, and store 3 bits among them. So black and red, right? So, and you decide which state out of these 3 will go. So advantage here is, suppose, right, MLC has reached its end of life, right? So you cannot because the margins are now no more, and you have used it so many times, 10,000 times. So should I throw it? Answer is no. You can downscale it, right? Update it on the fly. For example, you cannot replace drive, right, all the time. So in space, for example, in space, if you have reached the end of life, what do? You do the downscaling. and still use it with a little bit reduced capacity, but you can still store reliable data. So that's one of the advantage of doing fractional storage. Just to, as a fun fact, right? These are the questions we ask as a research group in our lab. Next, look at the other, but any question on so far the topics that we covered? So I hope by this time you understood how we store multiple logical bits on a same set of physical cell, right? So we are not doing anything in the hardware. Hardware is exactly the same. Whether you are using a SLC memory, whether you are using a QLC memory, your hardware looks exactly the same. Maybe the charge pumps will be a little bit more powerful for QLC because you have to go to higher voltage. Maybe your programming algorithm will be a little bit different, but in terms of pure silicon point of view, it is exactly the same. Now let's look at some of those operations, how we'll do read-write operation on array level, right? So this is your array, NAND array, one full block, and you want to read one page. So word line 1 you want to read. So what will be your biasing scheme? Suppose this is an SLC memory. You have program voltage 0 on and maybe 3 volt. So you'll put some intermediate voltage here, but here you have to put really high voltages. So these are the word line that is selected for reading. That has to be put in a lower voltage. The word line that are unselected, that has to be put in a pass mode, right? You have to pass the current. So this will be your biasing scheme because current has to flow in this column. So current should be gated by the cell you are reading. It should not be gated by other cells. So other cells should have gate voltage very high, right? So in other words, if you look at here, so here this is the selected word line. You put reference voltage, which will be low voltage, so 1 volt, but you will put high voltage. Pass voltage will be more than the highest threshold voltage in the array. Suppose your highest threshold voltage is 4 volt, right? So pass voltage has to be at least 4.5 or 5 volt, so that whether it is erase or program, doesn't matter, it should conduct on all the unselected word line. Only the selected word line will decide whether current will pass or not. That's how we read the particular selected word line. Now what is the problem with this setup? You never did it when you talked about SRAM or DRAM, right? SRAM or DRAM, whichever row you want to read, just look at that row. Other row doesn't see anything. But NAND, because of cost cutting, right? Cost cutting means making things small. You have to remove source line. All this problem comes because your source line is here. The ground is only here, right? There is no intermediate ground. So what is the problem with this set?
Change the state.
Yeah, there will be a lot of disturb, right? Because when you're reading this word line 1, the unselected word line can get disturbed. We are putting high voltages. So that means, suppose you have a USB drive and you are reading only one song again and again. Which means other songs will be corrupted, not the song you are reading. You see what I'm saying? Because suppose you are reading this word line, right? Your song number 1 is stored in word line number 1. Your song number 2 is stored in word line number 2. Next song, right? That's next song will be corrupted sooner. Okay, so that is the disturb mechanism. Maybe in the next class we'll talk detailed about array level reliability issues. But today's class is about biasing condition. How we'll read in an array. This is how we read. You read word line 1, you have to put high voltages on the unselected word line, which is called pass voltage, VPass voltage, because it has to pass the current, right? Because the way we read, we see whether bit line is conducting or not, right? So if this cell is in the erase state, it will conduct. If cell is in the program state, it will not conduct, right? So that's how we'll read. And for that, the other series connected cells should not be the bottleneck. That's why we put high voltage to allow current passing. So pass voltage needs to be higher than the highest threshold voltage in the array. So that's the criteria. That may cause sometimes disturb in your array. Questions? Okay, so now you can have read margin. So you have erase distribution, program distribution, you put them separate so that when you apply a reference, you can distinguish them accurately. But if you know that, okay, in the array you target 3 volt, but you know some cells can go 4 volt, right? Then you need to design your pass voltage even higher than that. So pass voltage will be a couple of volt above than the threshold, maximum threshold voltage you target to account for this distribution weight. So this 5 volt is here as the pass voltage in this array, and then you have margin for reading arrays, margin for program. And why these margins are important? Because during read there is something called read noise. When you read, cell threshold voltage can fluctuate because of noise, right? So that's why we need to keep some margin during read. Okay, so I think this is one thing I wanted to cover in the previous class. We talked about cell reliability. All those issues will come in. So one is called random telegraph noise. That means when you are reading, right, current should flow if it is on. But what happens is if these oxides are having defective, this electron can get trapped or detrapped, right? It will cause this kind of current fluctuation. So that means when you're reading, sometimes a high threshold voltage cell may appear at low threshold voltage, or a low threshold voltage cell can appear at the high threshold voltage within some range. That's why you need to keep some margin, right, for accurate reading. So that's one thing I wanted to say about random telegraph noise. All those things are important to for reliability of a cell. And this noise will increase with lower technology node. For example, if you compare 180 with a solid line, the noise level is low. If you compare 45 nanometer node, the noise level is high. Can anyone tell me simply why? Why for a lower technology node, noise level is high? It's all about area, right? So if you look at effect of one electron on noise, so Q equal to CV, right? That's the fundamental equation in college. So delta Q equal to delta V. Delta V here is the threshold voltage. So suppose you have only one electron getting trapped or detrapped, how much impact it will have? So delta VT, because of one electron, is Q, charge of one electron, divided by C. Now C for lower technology node is very small, right? 45 nanometer by 45 nanometer. That means this Q impact will be very, very high. So that's why this line is getting wider. So noise means most of the limit is one single electron getting trapped, single electron getting detrapped. How much fluctuation you expect in the ability. So that's the random telegraphic noise but versus technology node. This will increase with program erase cycling, because with program erase cycling you create trap sites. The oxides become defective, it's more likely that electron will be trapped or detrapped. And also it depends on the temperature. Okay, with lowering the temperature, red for example, you see this, an electron when it is trapped, it remains trapped for longer duration. That's why this signal, right, this level from this, how long it is there, that increases. If it is a higher temperature, it can trap, detrap, it can trap, detrap much faster rate, like thermal ones. But this is the telegraphic signal. Right? From the shape of the signal, the name random telegraph noise comes. This looks like a telegraph signal. Okay, so that's pretty much I wanted to say, that during read, this noise becomes important. And during program, right, suppose you have a program, we'll be done in 10-15 minutes, but I just want to finish up this operation. So program is the critical, right? Specifically, if you look at multi-level cell, because you have to shape up the distribution. How will you do it, right? Because you have to make your distribution narrow. So that's where, let's understand this part. So you have to write this page data, right? 1, 0, 1, 0. So that means first cell, I want to keep in the which state? Suppose the SLC. I have to write data in SLC mode. First cell, 1, right? 1 means erase. So I have to keep it in the erase state. That means I don't want any electron injection. Second cell, the blue cell, 0, right? I want to program it. But both of them share the same order line. How I'll do it? Because to program this blue cell, I have to put 20 volt. When I put 20 volt, how I should prevent programming on the red one? 20 volt. 20 volt means erase. So I have to keep it in the erase state. That means I don't want any electron injection. Second cell, the blue one, 0, right? I want to program it. But both of them share the same order line. How I'll do it? Because to program this blue cell, I have to put 20 volt. When I put 20 volt, how should prevent programming on the red one? Because I have to program parallel.
They're on the same, are these on same paper, silicon substrate?
Yeah, same silicon, same metal wall. The array, right? This is an array. And I have to program together. Any idea? Yes.
You like using with the bit line?
Yes, this is true bit line. So we put high voltage in the bit line. So at the end is the voltage difference between word line and the channel. If the channel is also high voltage, right, then it will not program. So that's what you will do. So whatever data you do, just like in other memories also, right? Whatever data you do, you put it in the bit line first. So that's data 1010, you put it here. So yes, you want to do, you want to keep it in the array state, put high voltage on the bit line, and you want to keep it in the, you want to program this string or this cell, to put low voltage on the bit line, 0 volt. 0 volt means your channel is grounded, so whatever, so word line going 18 volt, this channel will see 18 volt on the gate, channel is 0. But whereas this one, right, bit line say pushing the 8 volt inside. So the channel will get 8 volt, you will see 10 volt, so with 10 volt I'm assuming. So it is the voltage difference. So that's what you do, because you have to write programming in parallel. You have to program entire page together. So that's the biasing condition. So you have to bias accordingly, and all the other word lines in the pass mode, so that this voltage passing, right? So or you can couple. Basically, capacitively you have to couple the channel to high voltage. Now, all this biasing condition is important, but more important is what are the challenges during programming? First challenge is precise control of the BT placement. Yes, I want to program this, but I want to program this with the 5 electrons. If instead of 5 electrons, 6 goes in, data is corrupted, right, in many cases. If it is QLC, for example, I don't have much margin. How do I ensure that BT placement is precise? This is one challenge. Second challenge is over-programming, right? Yes, I want to program with 5 electrons, I don't want to keep going, right? Say 6 and 7 electrons. For example, there can be some cell which starts with very low VT. Some cells can start with very high VT. That means not all cells will require same amount of electron to get the same VT level. Right? So some cells will require higher program pulses, some cells will not. So I need to stop programming for some cells. Right? I have to treat, say, if it reaches this program threshold voltage, next program pulse should not affect it. So those kind of controlling I have to do. This is called avoid over programming. Maintain tight distribution for this distribution. All these states should be tighter, and minimize the cell-to-cell interference, because when I'm writing with high voltage on this word line, the cell which is already programmed in the next earlier word line can be affected as well. So all those things needs to be taken care of, and that's why industry, irrespective of whatever company it is, they follow this scheme. It's called incremental step pulse programming scheme. So I'll stop it, I'll explain this, and then we'll be done for today. Okay, so what is this incremental step pulse programming, or ISPP? Very important concept for programming aspect of NAND. So this is how it is. So your starting distribution is wide. Once there is no charge on the gate, some cells will still have higher VT, some cells will have lower VT. Can anyone explain why? When there is no charge on the gate, there is no charge on the floating gate, why threshold voltage will be different? Just process variation, right? Some cells can have higher doping, some cells can have lower doping, some cells can have lower thickness in the oxides, some cells can have higher thickness. So this is manufacturing variation. We are making millions of bits, right, in one array. So that distribution is reflected here. The process variation, which is fundamental variation due to fabrication process, right? You cannot make all the cells precisely, say, 6 nanometer thick tunnel oxide. Some tunnel oxide will be 7 nanometer thick, and that will change the threshold voltage, right? Some can be 5 nanometer thick. So yeah, so that is the initial variation. You cannot control that, but you can control this. You can make your program threshold voltage much tighter, because if a cell is in the upper tape, right, or high threshold voltage beginning, you need to put less electrons in its gate. If a cell has starting with a lower threshold voltage, you need to put a little bit higher electrons on it. So you compensate for it, right? So that's where you can do something called program and verify scheme. So this is the scheme. So first you program with a 15 volt, and next step you verify if a cell has reached their threshold voltage or not. So what is verify? Verify is just like a read operation. You put a threshold voltage or reference voltage and see who is conducting. If a cell is conducting, that means it requires still another program pulse. If a cell is not conducting, that means it has reached its threshold voltage. Okay, so you do program, verify, and next time you increase your programming pulse by 0.5 volt. And that is very important. This programming step, right? Delta BPGM or delta program pulse is 0.5. That means your width will be in the order of 0.5. If you increase, right, from 15 to 17 directly, then this width can be in the order of 2 volt. Because how you are stepping up the voltage, programming voltage, that will decide how wider is your program VT is. Okay, so if you go with a smaller delta, right, 15, 15.5, 16, 16.5, what is the problem? Problem is, yes, you can make things narrower because you are finer controlling the programming, but you will pay price in terms of latency. Your programming will not be done in 1 millisecond, it will go 5-6 milliseconds. And that's precisely happens when you go for higher logical scale. But QLC takes 5-6 milliseconds to program, whereas SLC maybe 500 microseconds is good enough. Right? So those are the trade-off. So you do, and this is how this ISPB scheme goes in. So if you want to really understand ISPB more, this is the paper from our group. We discussed this scheme very well, but you just see here how exactly happens programming in a different loops, right? This is 4 loops. One loop consists of program pulse and then verify operation. Program pulse, verify operation, like this. Then after first loop, your program distribution will look like this yellow thing has been programmed. This is just the position, right? If there was no verify, right? If you keep giving these pulses without this verification, this is how erase distribution will do. It will not be tighter. Why this cell distribution is getting tighter? Because after every pulse you verify, and if you see that okay, a cell has reached threshold voltage, you put high bit line voltage. If you put high bit line voltage, that means next pulse it will not see. It will prevent further programming, just like you prevented programming on erase cell by putting high bit line voltage, right? So whenever you decide, okay, this cell has been reached its threshold voltage, so put the high bit line voltage, and that's how you lock those cells out from further programming. So this is the algorithmic way to fight against natural variation. Your natural variation is wider, but you do program verify this kind of algorithmic way to tighten the distribution, and the less pulses you choose, less step you choose, this distribution will be much more narrower. Or more time you spend to program, this final distribution will be much narrower. So this is final last thing about erase. Erase is all about putting high voltage on the bulb. There is no need for precise control or anything. You just put flash erase. Everything should be erased. So it's one step you can erase, but still it will take some time because you need to take out, right, all those stored electrons. So you need to give some time to erase the substrate voltage and allow those electrons to take out. So that's pretty much last slide. This is the summary of all the biasing condition during read. During read, your pass word line, right? Unselected word line should be at higher voltage, and selected word line will go reference. During program, also the selected word line will go very, very high voltage. You want to program, unselected word line should be in the pass mode, and in the erase, the selected word line will be grounded, substrate will be high. That's how you erase all the word lines together. Yeah, I'll stop it here. And I think some of this biasing condition and all will come back to you in the form of multiple choice questions and all as you go forward. We'll see after this break. So I wish you all a very good, refreshing spring break. Okay, we'll meet after this break.
Yeah, this is getting close.
Thank you.
3:30 because of the light.
Thanks.
Like my brother who lived a bunch of here a while.
So like they've never seen that before.
Right.
I'll give you your chip.
I would have campus closed.
I've never heard of a campus closing because of lens in general.
It wasn't
Yeah.
like.
I think you can read a couple of words.
I mean, like,
Let me know because
it's just crazy.
all you need to do is
I will
just
campus closure.
provide VCC ground and address line. You can put them ground
Right now?
physically. You don't need a microcontroller actually.
Okay.
Just physically put all those address lines to ground. Put VCC and ground and check what is the status of data lines.
Okay.
Multimeter you can check,
Yeah.
right? Are they at 0 or ground?
Okay.
So that will tell you. But you have to enable the chip. Chip enable has to be on.
Yeah.
And the output enable has to be also active.
I wanted to
Yeah.
take a crack at some bare metal C programming. That's why I used
Yeah. No, I think you didn't need any programming. Just the hardware you can do that.
Yeah.
Yeah, programming you need if you want to automate that process.
Yeah. Then I emailed you about the vector multiplication thing.
Yeah.
How far out of the realm of possibility do you think? Like I've been playing around with LT Spice, and I was wondering if, I mean, I could build like a small three-dimensional NAND.
Yeah. It's possible, quite possible.
Okay. And then I mean, I just found out you can. I mean, I guess it makes sense. But you can play around with LT Spice via Python.
Absolutely. Absolutely. Yeah. And I have a student who knows some of those spice on. I think we have a better H spice or
H Spice, yeah. That's what they.
CSU. CSU has a license on.
Okay.
Yeah.
Cool.
So you can use them. I think I can put you in touch on one of my student who uses some of those spice monitor.
Okay, that'd be cool. I'll send you an email about that then.
Yeah, but at least is fine. The free tool, you can start with that.
Yeah. All right. Well, enjoy your break.
Yeah.
Hopefully it's not so windy anymore.
Oh yeah, it was very much my last time.